Hi, so this video we're going to be covering the concept of springs. They're really useful in all types of games and they pretty much have like a million applications, but it's kind of hard to derive a really good spring equation. You can find stuff on Wikipedia, but I don't think it really does a good job of explaining how we get to those equations. So hopefully this video is going to show you how we actually get from something as simple as Hooke's law. If you've ever heard of that, don't worry if you haven't, we're going to cover it in the video. To this time-based equation that you might find on Wikipedia that looks very, very messy. So let's get into it, and we'll start off with Hooke's law. Now the basic equation is as follows, and I just want to get my, I guess we'll start with a laser pointer. The basic equation is as follows. It's F is equal to negative K times P minus R. Now, K is a spring constant. Normally we put that value between 0 and 1, but technically it could be above. And P is the current position and R is the rest position or the target. Now I would normally call this a target because a spring, and one of its most useful things, is that it's a dynamic thing. So you, for example, you might set a spring to a camera, so it provides that smooth transition to the camera or animations or whatever, but you have a dynamic and moving target. So that's why I'd normally use the word target. However, the value t is going to come up later because we're going to use that for time. So for now we're just going to set our target, or as I said, rest position, to r. So really what this is, p minus r, is the distance from the target, or if we're working with vectors, it's the vector from the target. But for most of these examples, we're just going with the number line, but I think it's going to be very clear because all this translates very nicely into vector math. Like you can literally just plug vectors into these final equations and the spring will work just fine. K, however, is definitely a scalar. It's just a scalar constant, as I said, usually between 0 and 1. So to use it, we have to run iterations, and we have to pick an initial velocity. I mean, in my examples, I'm going to use a velocity of 0. I'm actually going to show you an example in a second, but we're going to use a value like a v velocity. We're going to have v is equal to v plus the force. So the force here is, remember, F, this Hooke's law. And then the position is equal to the previous position plus the new calculated velocity. So we have an initial velocity. We update the velocity by taking the old velocity and adding the force to it, giving us a new velocity, and then we update the position by taking the old position, adding the new velocity to it, and we keep running these iterations over and over. And I'll probably put, I probably have already put it here, but just a little like an Excel video showing deriving that. And what you'll also see from that Excel video is that our end result, and I just once again want to get my pen, our end result is motion. And I'm just going to, I know we set the target, I believe, in that video. The values I think we used are 0.1, the rest for the constant, sorry, the rest position was 5 and the starting position was 6, and the starting velocity was 0 in that video. But I'm just going to pretend that our rest position was 0. And basically what happened is we started and then we get some motion, but it never actually goes to 0. It just goes up and down, almost like a sine or cosine wave. It just goes endlessly on and on and on. So that's a pretty big problem, because obviously with the spring, the motion that we really want, and I'm just, I guess, kind of writing over top of this, is something that does approach our target, right? It gets closer and closer and eventually just kind of settles there. So that's the real motion that we want, but this is what we have. So we need to make some adjustments to Hooke's law, but before we do that, let's just get basically some more intuition on it. So let's say on iteration 1, we have our rest position over here, R, and we have our initial position, P, and our force and velocity are set to 0. So we know our P dot R is represented by this blue arrow here. For iteration 2, we can calculate our first force value. So that's going to be about, if we're using, let's say, 0.5, that's going to be this green arrow here is the force value, right? Because that's 0.5 basically times this blue arrow. So that's just half of the blue arrow. Then we know that velocity is equal to, well, 0 plus force, so we have a red arrow that's the same as the green arrow, and then we know that our position is equivalent to the old position, which remember was up here, or rather here, plus the velocity, so we get a new position right here. Oops, I don't know what I've done there. So that's where we're left in that iteration. So for iteration 3, we now have our old position is where our new position was last time. Oops, so our old position is now here, right? This is our are now our, where did it go? Yeah, this is now our old position. And we take half of that, right? So half of our old position in blue is once again this green. So right, about half there is about 0.5. So that's our green. We add that to our old velocity. If you remember looking back at our velocity vector, it's about that length, but we now add this green vector to it. So we have this whole thing. And then we take our old position, right? Old position plus this new red vector here, which leaves us with that. For a final iteration, just to kind of show you once again, we have now a position. This is past R, so R is here. Our new position's all the way out here. So we actually now have P minus R that's going in the opposite direction, this blue thing. So F, half of that, once again, 0.5 over here. We get F, and we have our old velocity, but this time we're adding our force to the velocity, but it's going in the opposite direction. So we're actually left with a velocity value that's still going in the same direction, but it's less than it was last time, right? So we took the 1, 2, and then backward step, but we're still technically going forward. So it's like a net, right? So we have a whole bunch of this direction, and then we have one negative going in the opposite direction. But that doesn't change the entire direction. It just slows down the velocity going in that direction. So we make a slight adjustment back, which leads us all the way over here. And our rest position is here. So we jumped from, as we saw, we're getting that motion of up and down, where this middle point is our rest. So we went all the way out here, and this cycle would continue on and on and on, as you hopefully saw in that little Excel thing earlier. So now we need to deal with, I said, as that problem of just going on and on and on and never actually approaching the point here. So to do that, we just add in another value. We add in another constant, beta, and we make it damp the velocity. And the effect that basically this has is exactly what I drew earlier. So we go up, and then it gets closer and closer, and eventually just kind of stays around 0. So we're just going to define x as p minus r from this point on. So x really is just, as I said, the distance or the vector, depending on what values you're working with, from the rest position. But yeah, as I said, it's just simply the distance from the target. And if we were to once again do an example, this time same values as last time, but beta is 0.1, then I'll once again put an Excel in the corner or something. I probably already put it here. But you can see that we get a situation like that. So there are some problems with Hooke's law. The first is that it's not frame rate independent. And the goal for the rest of the video, I shouldn't say the real problem is that it's not frame rate independent. That's really like the main problem. And that's the goal for the rest of this video, is going to be to make an equation that is based on time and is frame rate dependent, or independent, sorry, I keep messing it up. So Hooke's law is frame rate dependent. We want to make an equation that is frame rate independent. And all I really mean by that is, because if we're doing iterations, say we're updating our Hooke's law, right? So we went over iterations, iteration 1, 2, 3, 4. If we were to do that based on frames, so we do that every frame, someone going at 60 frames per second is going to have a much, a spring that ran for a lot longer and has probably done a lot more, or potentially reached its target a lot faster than someone running at 30 frames per second, even though the same amount of time went by. And that's no good for people who are animating or whatever, because you want stuff to look the same no matter what computer is running it. And no matter the settings and what have you. So we definitely need to deal with that. So the first thing that we're going to do is we're going to recognize Newton's second law. We know force is equal to mass times acceleration. We can set this equal to Hooke's law, right? Mass times acceleration is equal to our Hooke's law that we talked about earlier, all the way over here, this guy. We can set them equal. And then we can just bring all of this to the left-hand side, leaving us with this here, sorry. And I didn't quite box that properly, but you get the idea. Now we have to make some slight unintuitive adjustments to this that's going to make our lives easier in the long run. Now you might be wondering, okay, why? But why would we ever, know or make these adjustments? And to be honest, from my perspective, I never really found a good reason to just pull these out of nowhere. I saw in Wikipedia, we're using the same kind of values that they use on the Wikipedia page. So they use like omega and zeta over here. They use all these values. So other than that, I just tried to kind of make these fit over here the same as the Wikipedia page. But if I didn't have that Wikipedia page as a reference point, I probably would have gone in just straight up with this, and we might have gotten a more difficult equation in the end, or it might have been easier, I don't know, but I just wanted to follow suit with Wikipedia, so I set my values similar to them by breaking it down like this. So we're basically left with acceleration plus 2 times omega zeta times velocity plus omega squared times x is equal to 0. And of course omega and zeta are defined here. Now we don't really have to worry about these anymore because we're just going to be using omega and zeta from this point on. But you might want to come back to this point in the video later so you can actually copy these down when we have the full equation, because omega and zeta are of course going to be in it. So a quick note on ODEs, right? This is an ordinary differential equation. Sorry, I guess I didn't note that. And it's an ordinary differential equation because, and I think actually I mentioned this later, so maybe I won't talk about it. Yeah, no, it's right here. Because position is equal to x, right? And we're looking for some function x of t. Velocity is, of course, the derivative of position with respect to time, so it's x prime t. Acceleration is just the second derivative of x with respect to time, or the derivative of velocity with respect to x, and we can use prime notation for that as well. So we can write our ODE as we want, or as x prime prime t, this form with our prime notation. And I think it becomes a lot more clear here that all we really have is just an equation that is a whole bunch of position equations that are all somehow related to each other, right? So we have x prime prime, x prime, and x, and that's really what we're trying to solve for, because we actually know what 2 times omega zeta and omega squared is. Those are, in the end of the day, constants, because we pick our k, m, beta, 2, mk, all those values. We pick all that, so it's just a matter of finding what our x of t is here, and of course our x prime and x prime prime. So before we continue any further with our actual ODE here specifically, I just want to make a note on linear combinations. So let's say that we have 2 solutions for our ODE. So let's say we found 2 different things that fit this equation for x of t. So we have h of t and g of t. So that means that we have h prime prime of t and h of prime t and h of t, and when we plug those in we get 0, and same with g, right? We have g prime prime of t and g prime of t, and g of t we also get 0. So if we're trying to find a general solution for x of t, right, so something that encompasses all the solutions, right, we know for a fact that we have h and t and g and t as solutions. We want to make sure that we're covering everything in our general solution, right? Our general solution should be able to have all the values that h of t and g of t have. So the question we want to answer is, if we do a linear combination, right, where c1 and c2 are just constants, right, so we have some combination of h of t and g and t, is that also a solution? And the answer is pretty simple. If we plug them in, right, so if we do c1 h prime prime of t, plug that in for your prime primes, and so really I guess I should just underline these and hopefully you can see what I've done here. We're just basically plugging in that combination with the prime notations in the proper spots. We expand it out, and we put them together in their separate groups, and then we factor out the C1 and the C2. Well, we know already these things over here are equal to 0, so C2 times 0 and C1 times 0 are of course going to equal 0. So yes, any linear combination of these 2 separate solutions is also a solution, and that's really useful because, as I said, it helps us find our general solution over here. So if we have 2 solutions, which we should, for this type of ODE, we need to make sure that we combine them. So now we can start to talk about actually solving for x of t, and the easiest way to do this is to follow suit with Euler. And what Euler would do is he would set x of t equal to something that's easy to take derivatives of, which is e, Euler's number, to the power of z times t, right? So of course that's pretty simple, and we're really putting a lot of hope, if you will, into the z value that's really going to make this e to the zt fit the spring that we want. So We'll start by taking the derivatives, right? So we'll find v is equal to z zt, a is equal to z squared e zt, and we can plug those into our ODE to have a form there. But we still don't know what z is, right? So that's going to be the next step, is we're going to be solving for z. So we can factor out the EZT, which just leaves us with this simple parabolic equation. We can use the quadratic formula to figure out the two solutions for z, which are shown right here. We should note here that there's actually 3 solutions to this, and this is where things kind of get a little hairy, if you didn't think it got hairy already. Specifically with this value, if we go back to this is in both of them. We have the square root of zeta squared minus 1. Depending on the value of zeta, we might have, so if zeta is greater than 1, we'll have 2 real roots, because if zeta is greater than 1, that means whatever that value is squared is going to be greater than 1. So we have something greater than 1 minus 1, which gives us a positive value squared, which is just a normal number. It's a square root of a decimal, but it's still a normal number. If zeta is less than 1, then we have 2 complex roots, because if zeta is less than 1, that means zeta squared is going to be a number that's less than 1, which means we have a negative number underneath the square root here, which is going to, of course, lead to a complex number, because that's an imaginary number then. So if zeta is equal to 1, then we only have 1 real root. So right, if we go back to this, if zeta is equal to 1, then that's just 1 minus 1. Square root of 0 is 0. So omega times 0, no matter what, is going to be, we're just essentially left with z1 and z2 are the same thing. So we only have 1 real root for that case. That being said, we really only care about one thing specifically in this video. There are a whole bunch of, as I said, steps, and this is where it gets really hairy for numbers 1 and 2. But we're going to be focusing mainly on 1 and 3. We're going to be focusing mainly on 2 in this video, the complex roots, because that's the situation where you're going to get something that goes below and back and da 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 da, because the other ones you'll just kind of get like a whoop or like something like that, that just very quickly gets to the to its target. So maybe, I don't know, maybe we'll go over 1 and 2 another day, but I think this video is going to be pretty long already. I'm looking at my timer and it says I'm at about 17 minutes. So there's no way I'm going to get into 1 and 3 as well. So we're just going to cover 2 today. So zeta is less than 1. Since we know zeta is less than 1, we can rewrite that square root aspect with the imaginary number pulled out of it, right? So we know that this is somehow going to be less than 1. So we'll just go ahead and we'll multiply this by -1, but we don't want to change anything. So of course we just multiply by -1, but then that becomes 1 minus zeta 2, right? Because if you put that in, that becomes -1 and positive zeta 2, which is just over here. And we can take out the -1, and of course we know our imaginary number is the square root of -1. So it's the imaginary number times the square root of 1 minus zeta squared. Then we have our 2 roots, right? We go back, if we were to go back those slides, these 2 roots here with our 2 imaginary number, complex number, whatever you want to call it, plugged in. We can plug those into our original x value that Euler gave us, the one that we started, so this guy all the way over here. So we plug those in and we get 2x solutions, right? We can split that apart, so we have the one part is split here and the other part is split here, and we do that for both of these. So we have to split here and a split here. We split those into those 2 things. We can apply Euler's formula, which we know is e to the imaginary number I times y is cosine of y plus the imaginary I times the sine of y. And so we can apply that. So if we go ahead and do that for those 2 x1 and x2 values, we find that we get this monstrosity. You can use the trig identities that cosine negative theta is equal to cosine theta and sine theta is equal to negative theta. We can get x1 and simplify that a little further to get rid of some of the, where would x1 be, to get rid of the negatives inside here and here. That makes our life a little easier later on. So we get x1 and we have x2. Now, a while ago we talked about linear combinations, and we're going to do like a neat little trick here. We're actually going to do a linear combination of x1 and x2, 2 separate linear combinations of x1 and x2 that keep them linearly independent, and then we're going to combine those. So we're actually going to find an x3 and an x4, and then we're going to do a generalized combination of those two. But we're doing this first initial combination to kind of simplify things. So you eventually kind of get to here, you can just read this over, but you get from this combination here to just this simple thing over here. Well, it's not totally simple, but it's a lot simpler than what we had before. And then we're in the next one for x4, we're actually going to get rid of the imaginary number. So, and we do that by having the 2 over 2i, 1 over 2i, and we're left with that. So we have x3 and x4 here, and they're both much easier to work with. So we have two independent solutions that are simplified and they're not complex. So we can now take x3 and x4 and linearly combine them generally, as I said. So we're going to plug in the general c1 and c2. So we plug those in, we do some simplifying, and we get this. So this is our x of t equation. The only things we don't know in it are c1 and c2. So we'll talk about that in a second. But in order to find these, we need to find velocity. So we just do that by taking the derivative of our x of t value. So we're taking this x of t value over here, finding the derivative of it, and that's a bit messy. This is probably the messiest part we have to do, but that leaves you with this guy here in the end. Then with some simple intuition, we know that at time 0 we're starting at an initial position and an initial velocity, right? So I guess I probably should have put x of 0 here, right, like that. So is equal to x naught and v naught for initial velocity and initial position. So we can use those to plug in to our x of t and our v of t things, right? So x0 is equal to x0, so e that simplifies to x naught is equal to c1, and we can do the same thing for velocity. So v naught ends up being equal to negative c1 omega zeta plus c2 omega square root of 1 minus zeta squared. Then we can sub in that x naught is equal to c1 into the above, and find, of course, c2, because we already know what c1 is, so there's no point in trying to find c1 again. So we plug that in. X naught goes for where our c1 was up here, right? These two plug in. We just simply rearrange, and we find that c2 is equal to v naught plus x naught times omega zeta over omega square root of 1 minus zeta squared. And there we have it. We plug our c1 and c2 values back into our velocity equation here, and our x naught or x of t equation here, right, for these c1 and c2 equations, and we're left with our final solutions, which based on time give us this nice function that slowly approaches our target, or 0 specifically, because x, remember, if you remember, x is always approaching 0 because x is equal to p minus r. So really, if you wanted to properly target, you'd take your x of t, right? So if you wanted to really properly have it, so like let's say you set your target at 1, you'd have 1 plus x of t, right? And that would make it approach. That would make it actually approach the proper things. So that's pretty much all there is to it, and that was a little messy, and I'm probably just going to switch over to an example here of actually applying it to code, and that'll probably be pretty much it for the video. So as far as the learning portion goes, so let's just head into the code, and I'll see you guys there. Okay, so we're back now in Unity, and all this is pretty simple. We're just basically applying those equations from before now into actual usage. There are few hitches here. The first that I just want to mention real quick is, because I didn't really go over this, is that zeta is equivalent. You can find all this on the Wikipedia, because as I said, Wikipedia kind of goes over it. I just don't think it does a super amazing job at driving it, but I mean, that's my own personal opinion, so hey. But basically they give you, this definition of terms, right? So we have zeta, and remember, we said zeta equivalent to their zeta and our omega is equivalent to theirs, so we're setting our zeta equivalent to the damping ratio and our omega equivalent to the angular frequency. And if you wanted to, you could go all the way back. Remember, we came up with terms for omega and zeta that were based on beta and mass and the spring constant and all that stuff. So if you wanted to go even further, you could do that. But I was just like, whatever, we'll just stick with omega and zeta. So as I said, that's that. Most of this is just basic setting stuff up. Of course, I'll post this in the description. One thing we have to be careful of is, because we didn't remember, I mentioned there are a few cases that zeta could be equal to 1, it could be greater than 1. We just want to make sure that if there is one of those cases, we don't do anything because we didn't learn how to deal with it. If it's less than 0, we shouldn't be dealing with that, so we're just going to set it equal to 0. Now an important point here is, because we're doing this by time step, we can't use just one equation. So the way we're doing this is we're continuously using these two equations here, x of t and v of t, but we're updating the x naught and the v naught, whereas before, so for example, when I did this in Excel, will it tell me the formula? No, that's Hooke's law. What am I looking at here? When we do it in this, was just purely the x of t function. I did it based on a time value that I could set, but since we're using change in time, we're just going to update those x naughts and v naughts. And remember, the important thing to remember is that x naught is the position minus the target. It's not just the position, it's the difference between position and target. So we update our x naught, we calculate our omega zeta, like our constants, things that are pretty constant. Once again, we're just looking at this equation, so we're calculating our x naught, we're calculating our omega zeta, because omega times zeta comes up a lot in our equations. We're calculating our C2 because that comes up a lot in our equation. I defined a new term called alpha, which is just this. It's it's everything except for the t there. I'm having trouble highlighting it. So it's omega times the square root of 1 minus zeta squared. So that's what alpha is. We're calculating the cosine and the sine terms, the exponential term, and then we're plugging both of those in and updating our position and velocity equations, and there we go. So in terms of actual application, I just decided to set the zeta value to 0.1 and omega to 0.5. I just wanted to show you a nice little spring thing, to show that it really does have that spring type motion. And it's actually really good that we probably have this delta time, because recording this, I don't think it's gonna hold it. Oh no, it's holding up okay, but you can see we're bouncing back and forth. We can change it up, and it really bounces in. It feels like a spring, and it gets closer and closer to our target here. So of course you can tune this a lot. It doesn't have to be as bouncy. You can make it maybe a lot smoother in its transitioning and what have you, but I think that's pretty cool, and as I said, definitely has a lot of uses. So hope you guys enjoyed the video and learned something new from it. Thanks for watching.